Okay, let me recall first some definitions. That square is simply a string of the form XX, and the square-free string is a string that does not have a substring that is a square. This is the topic that we considered yesterday and today in morning, and it is simple. For example, these are squares, and such string is not a square, for example, is not square-free, for example, and do we have strings that are square-free? And this was already considered. I recall briefly that every string of a binary alphabet, sufficiently large string, of course, has squares, is not square-free. But Excel 2 in the very beginning of 20th century showed that even for a 3-letter alphabet we can construct a square-free string of arbitrary length, even infinite string. And here we consider algorithms that decide whether a given string is square-free or not. And we do that in an online approach. And the main definition is what is online square detection, and we say that an algorithm online detects squares if this algorithm reads an input string sequentially from left to right, and when it reads a consecutive letter, it decides whether a given string is square-free or not. Consider, for example, the simplest algorithm, of course an efficient algorithm that works in n-cube time. This algorithm reads a letter, and if a given string was square-free before, then and if this string is not square-free, then of course a given string has a square that is a suffix of this string. And this algorithm simply considers all suffixes of a string and naively checks whether they are squares or not. But of course we can do better. But it was proved in 1985 in the paper of Main and Lawrence that in the case of unordered alphabet we can't do better. We, in the worst case, must to perform n log n comparisons to check whether the string is square-free. And initially the study of online square detection was inspired in the field of artificial intelligence, where it was some tool for another huge algorithm, and the authors of this algorithm considered some construction that led to an algorithm that works in n log squared n time on unordered alphabet. Of course, this is what?
Is it time for whole string of length n when we add letters?
Yes. When I say n, I mean the total length of the string read at the end of algorithm. No, this algorithm is online, so we read string while we don't read n letters. But this is for unordered alphabet. Further, another authors improved this algorithm for working faster on ordered alphabet. But indeed, for ordered alphabet we can do better. And further was proposed an algorithm for online square detection in n log sigma time on ordered alphabet. But actually, there was already an optimal algorithm for unordered alphabet, and it was proposed in 1996. But this paper is not about online square detection, so these authors and I did not know about this for the time. This is optimal algorithm. It is practical algorithm. It can be used. But I did not know about this, and I found another algorithm with the same time complexity and using another approach. Oh, this algorithm is impractical. It is only a theoretical algorithm. And using an approach that is not as approach as Pasteliki and Breslau used, I found an online algorithm that detects squares in n log n time. And due to this lower bound, this algorithm is optimal for unordered alphabet. Using the same tools that I used here, I later found for ordered alphabet an algorithm that works in n log sigma time, and it is practical algorithm. But I do not consider this here.
What do you mean by practical?
practical. It can be implemented and use little space. This algorithm is impractical since it uses 4 suffix trees of length n with additional information and a couple of arrays of integers. And so for huge input data, this is bad to use such large memory. But it is linear.
And what's sigma, by the way?
Sigma. Sigma is the number of distinct characters in an input string. Sorry. It appears only here and here and will not appear anyway. To introduce my auxiliary data structure that is used for construction of my algorithm, I recall some other definitions. A border of a string is simply a string that is proper prefix and the proper suffix of the string. For example, for a string ABCA, BCA, we have 2 borders. The first border is A, and the second border is ABCA. This is simple. The occurrences of this border overlap, but this is no way. Let me state the main lemma that will be used. Let text be a string of length n. This will be exactly the string that we analyze. And suppose that text 1 and minus 1 is square free. Then we append the letter to the string and appears 1 new square, maybe 2 new squares, actually 1 square. That for some k, the suffix text kn is a square. And suppose, let us choose 2 integers ij such that k lies in the interval ij, and the length of the interval ij is less than the length of the interval j plus 1n. Consider this picture. On this picture, we divide the string x on 2 substrings, x prime and x prime prime, accordingly to the position of an interval of the interval ij. That we can do that because of this inequality. The length of ij is less than the length of j plus 1n. So we can divide x on 2 substrings. From this picture we see that x prime prime is the border of text j plus 1n. But since of that text 1 and minus 1 is square free, we can state a more strong statement that x prime prime is actually the longest border of text j plus 1n. This is not difficult to prove, but it needs some thinking. I will not do this here. This fact relies on the fact that text 1 and minus 1 is square free. It is proved by a contradiction. So our main auxiliary data structure that is used for square detection is the catcher. Catcher current block ij of text 1n. It will catch squares that appear in the string. For a correct work, the catcher needs that text 1 and minus 1 is a square free string. And as I noted, the length of the interval ij must be less than the length of the interval j plus 1n. The length of this interval is called the length of the catcher. And the catcher works in the following way. When we read the letter and append it to text, and if the text contains square suffix such that the leftmost position of this square lies inside our interval ij, then square catcher must detect this square. This is a trap of the catcher. It catches squares that lie in ij. It's simple, of course. Now about an implementation of the catcher. Actually, the implementation is very simple, but the proof of its time complexity is not so simple. Our catcher maintains 2 variables, b and s. b is the length of the longest border of text j plus 1m. We can compute it online by the algorithm of Knut, Morris and Pratt. We can compute it online in n minus j time. Now to define S, we consider two cases. The first case is when once we computed B, we see that B is the length of potential x prime prime. Maybe here on this picture we have a square, but maybe we have not square, but we have the length of x prime prime, the longest border of text j plus 1 n. And we see on the length of x prime, it is here, n minus j minus 2b. And if we see that the length of x prime is less than the length of ij, then probably we can catch a square if it is here. So in this case we compute S by a naive algorithm. S is the longest suffix of text ij and text I n minus b. Just we compute x prime explicitly by a naive algorithm from right to left. In this case S is equal to 3. We see that x prime can be placed inside ij, and then we compare c, c, b, b, a, ey, and see that S is equal to 3. The longest suffix of text ij and text n minus b, text j n minus b. So given b and a, we can catch the square and otherwise S is equal to 0 if we have no place for x prime. Once we computed b and s, we can catch a square, and this occurs exactly when 2b plus s is greater than n minus j. This is the situation pictured here. The time complexity of this algorithm. This can be simply implemented if we know the algorithm of Knuth-Morris-Pratt. But it is also the simple algorithm. It uses n minus j space and works in n minus j time. But it is not obvious how much the overall computation of S takes. It can be proved that it also takes all of n minus j time. That's because we not always compute S, but sometimes we ignore S and assign 0 to S when we do not need it. But this is not obvious. Now we have this tool, an auxiliary data structure catcher, the catcher. And the idea how to catch all squares, just how to detect squares, is to locate the number of catchers on the whole string in such way that in intervals that the catchers cover, covers the whole string, except for text n. And let me describe this system of catchers. First, for every k from 0 to log n, we have 2 or 1 catcher of the length 2 to the k. The first catcher the first such catcher has the length 2 to the k, and it is aligned on the border of 2 to the k. As a border, this number. It is in this position exactly. And if p sub k, this number, is even number, then we have another catcher that is a neighboring catcher. It is located to the left of the first catcher. Sometimes we have not this catcher. Maybe it is not obvious that this system covers the whole string. Here the picture. How does it work? Here for k that is equal to 2, we have 2 catches of the length 2 to the k, 2. The first catcher is a neighbor of the second catcher, and the main observation here is that the catcher of the length 2 to the k is located on the distance of 3 times 2 to the k from n. Here we see that this catcher is located on the distance of 4 from n. This cache is located to the distance of 8 from n. That is, if we know that every cache of the length 2 to the k is located at the distance of 3 times 2 to the k from the end of the string, then and the maintains of this cache require all of 2 to the k time and space, as the lemma states that was before. This is the whole algorithm for square detection using caches. And on every iteration, this algorithm considers all k from 0 to log n, and if it is needed, and creates the caches if it is needed, and removes the previous caches of the length 2 to the k. Let us consider the time and space complexity of this algorithm. As I said, the maintains of the cache of the length 2 to the k requires all of 2 to the k time and space. That's not because the length of this cache is 2 to the k. That's because the caches of the length 2 to the k are located at the distance of 2 to the k, all of 2 to the k from the end of the string. That's why the maintenance of this cache, these caches requires all of 2 to the k time and space. Thus, all caches take all of the sum for k from 0 a geometric series space, and it converts to all of n. It is linear space. To maintain all caches of the length 2 to the k during the whole algorithm, I recall that at any time we have at most 2 such caches, but notice that during the whole algorithm, 2 caches of the length 2 to the k do not intersect. So when we execute an algorithm, we have at most n over 2 to the k caches during the whole execution. And every such cache requires 2 to the k time. So to maintain all caches of the length 2 to the k during the whole algorithm, we require all of n time. As k is from 0 to log n, we have an overall of n log n time and linear space. There are no open problems still. The first one is, can we do better than n log sigma for an ordered alphabet? That is not considered here in this presentation, but it is an important case. And the second one is the problem of an efficient implementation of rollback operation that was considered today in the morning. And this algorithm is required for algorithms generating square-free strings. And that's all. Thank you.
So you report, when you detect a square, is it the shortest one? Is it the, because there can be several squares ending in this position, of course, so can you say anything about this, which square you detect?
Yes, we can report the length of the detected square.
Report the length of what?
Of the detected square.
Yes, but is it the shortest one or an arbitrary square?
An arbitrary. Yes, this is the first one. If the string was square free and we append a letter, we will have
a unique square. If you append a letter to a square to a word, we will get a unique square.
Yes.
Because otherwise the previous part is not square. If you append just one letter to a square to a word, you cannot get several squares. Because the longer one would contain the square before. Long square contains the short square as a suffix.
No, but it's not like the shortest is inside the
the repeated unit. They can be like actually they can be logarithmic number of squares ending at.
Yes, but not. But since you work online and you know that the longest prefix of this word is square free, so we have a big square.
So we have to go 4 squares and with the plus 1 is an answer.
No, but even if you can add one letter and have a logarithmic number of new squares.
No. Just one.
It is true, of course, what you say, but the nature of this algorithm is it works online, so you read your law from left to the right, and you stop as soon as you discover the square. So the square that you will find by this algorithm is the very first square from the left of the law. It may be.
And this is
there may be
it is
different squares after the longer or shorter.
maybe the earliest, the square which ends at the earliest time is unique.
But this is not obvious. This, you must prove it.
Okay. And the other question is about the alphabet size. So I just to make it precise. So the algorithm doesn't depend on the alphabet size, if you understand.
Yes, it does not depend on the alphabet size.
So because you only do
Only comparisons on equality or non-equality of letters, and nothing is.
Why do you say that the other person is impractical and you respect? Do you have any like experiment?
No. I read it and I realized that such an amount of.
Your multiplication constant is huge and you even don't know it. Or
I tried to calculate this constant, and when I used a result for space-efficient implementation of the suffix twist, this led to something as AT or something such.
for your algorithm.
Constant, no, for this algorithm.
And for your algorithm?
And this algorithm is lightweight algorithm. This use 2n integers at least, and this all, I think, maybe 4n integers.